At Accelereyes, we're interested in GPU software and in making productive GPU software specifically. And in this session, we're going to talk about how MATLAB can run on the GPU through our product, Jacket. In this session, I'm going to talk about Jacket for MATLAB and how it's able to enable standard codes from MATLAB, your optics codes, for instance, to run on the GPU and to be accelerated. I'm going to talk about G4. That's a very powerful construct available in Jacket that lets you run many iterations of a for loop simultaneously on the GPU. I'm going to compare it with the Parallel Computing Toolbox's alternative GPU solution. That's, as many of you may know, MathWorks themselves has copied some of the features of Jacket into the Parallel Computing Toolbox, and we'll talk about why you would want to still use Jacket. And then we're going to talk about moving into the future and things that are cool, upcoming, and other things you can do with GPU technology. And finally, after we finish with the slides, we'll share some optics applications and run some code to show you how it all works and to give you a nice introduction. To start with, this is a nice example because it demonstrates a situation we find all sorts of customers in. This is an image processing application, but there was a Northrop Grumman Corporation team in Falls Church, Virginia, that wanted to do UAV imaging. And so they had a particular application where they fly these UAVs and they want to detect ground vehicles. In this scenario, their baseline performance, they had some CPU code using Intel performance primitives that was running at 4 seconds. And they needed to accelerate that by 10x to get it to be real time so that the UAV could actually process the high resolution imagery with the ground vehicle detection algorithms in real time. Again, the problem was that this highly optimized CPU code was just too slow, 10x too slow, in fact. And the other problem was that when they tried themselves to do GPU computing by writing their own CUDA code, they just were very frustrated because the algorithm calls for many small image patches. In those small image patches, if you sort of just do it the straightforward way in CUDA yourself, don't perform very well. In fact, they're slower than the CPU because GPUs like to work with large pieces of data, and all of these small image patches processed in a standard loop were just not working out very fast and were performing too slowly. So their solution was that they started using Jacket. And in fact, this group had a combination of both MATLAB code as well as C++ code. They were using a combination of both prototyping with MATLAB code, but then deploying with C++. So the first solution was to take that MATLAB code where the prototype existed and to use Jacket to avoid this low-level hassle of raw CUDA. So you can really quickly, with Jacket, in a matter of a few hours, start to experience GPU acceleration without the low-level and very complicated details that are involved with writing raw CUDA code. So that was the first solution, and then they started to see some nice speed-ups, but they knew that it wasn't as much as they wanted. So then, in fact, they just simply wanted to have, these were researchers who had all sorts of other projects on their plate and didn't want to spend, their full attention on writing good GPU code. So they hired our consulting services, and with our consulting services, we were able to notice that the true problem with the small image patches is easily addressable through the use of the G4 loop. So our GPU consulting experts were able to go in and simply use the G4 loop. It didn't take us very many hours at all to do that for them. and suddenly we were able to get the code result of 0.4 seconds achieved, and the whole project lasted less than a month, and that acceleration was something that then they could rely on, and they won the next phase of funding for. So this is an example of how these sort of productive GPU software solutions are valuable and can save a lot of time and hassle, and actually result in speed-ups that are seemingly unachievable sometimes. So let's talk about just the general concepts here of how Jacket works for M-code. So with Jacket, Jacket uses the standard object-oriented approach that's available to all MATLAB customers. We create new objects or data types in the MATLAB workspace called G-doubles. When you install Jacket, you get access to G-doubles, G-singles, essentially GPU versions of the CPU data types, and those GPU objects are then overloaded on any subsequent operations. So in these 6 lines of code, it's a very simple algorithm that estimates pi algorithmically, and in the 2 highlighted lines, that's where the data creation is occurring. X and Y end up as GPU, double precision GPU random vectors of 20 million random samples each, and those 2 lines are the only GPU-specific lines of code in this 6-line sample. The only GPU-specific functions within Jacket are those that deal with data creation, such as G-double, G-single, G-ran, G-ones. These where you create or transfer data to the GPU. Those are the only Jacket-specific commands. All other commands use the MATLAB overloading features, and so you can run existing code on the new GPU objects without any change. Here are the matrix types that are supported in Jacket: the G-double for double precision, G-uint, and then it could be uint8, uint32, so forth, for integers, single precision, signed integers, as well as booleans are all supported. Jacket also supports n-dimensional matrices, so from vectors to 2-dimensional matrices to volumes to n-dimensional. You can do everything that you would normally do and interface with MATLAB data structures you can do with Jacket, and it all occurs on the GPU in a parallel manner. So here are some subscripted assignment or referencing constructs, all n-dimensional as well for easy data manipulation. Finally, like I said previously, these 3 lines of code are actually the algorithm lines of code. They're just standard MATLAB lines of code. There's nothing GPU specific about those. But by virtue of the X and Y being GPU data types, those 3 lines of code will run on the GPU because of the data type. So, for instance, on the distance to origin line of code, since X and Y are both G-doubles, those multiplications and the addition as well as the square root all occur on the GPU and get assigned into the variable distance to origin, which is stored in the MATLAB workspace as a GPU variable. So if the inputs are GPU variables, then the outputs are GPU variables, and so forth. In the next line, since distance to origin is a GPU variable, that logical operation of less than or equal to 1 will occur on the GPU, and then the result is stored in the variable is inside, and so forth. The GPU computations are propagated throughout the code. If you want to return a result back to the CPU, you simply cast the matrix back to the CPU. So, for instance, the end result of this 6 lines of code, pi, is going to be a G-double stored on the GPU. But if you want to bring pi back to the CPU, you just cast pi back by using the double casting command that's available in MATLAB. So again, no GPU-specific stuff was involved. There is no development of these low-level kernels, no threads, no blocks, no warps, just really regular MATLAB code. And Dr. Kevin Tubbs talked about a lattice-Boltzmann model that he was developing. He says very little recoding was needed to promote that model to run on the GPU. So that's really the core concept. It's you take your code, imagine your own optics application. You may have, instead of estimating pi, you're going to be doing some FFTs and some interpolations. You just simply take the input data that you have, cast it to those GPU data types, and then you don't have to change the functional code, but by virtue of the input data being of these GPU data types, the functional code will now execute on the GPU through Jacket and run in a fast manner. Once you've got the basics down of this data casting, there are a few more advanced features that are very powerful, and one of these is the G4 loop. Here I showed two different for loops. One is a regular for loop. Both of these, we assume that A, B, and C are GPU data types. They're all G doubles. Both of these loops produce the same result, and both of these loops are completely valid and run just fine, except the first loop runs each of the iterations sequentially in 3 separate kernel launches that are all done serially, whereas the G4 loop is able to combine all of those operations into one kernel launch and launch essentially all iterations of the loop simultaneously. And so just to spell that out, a regular for loop is going to do the first iteration. This is a simple matrix multiply example. So the first iteration is going to multiply the first slice of A by the vector B and produce and store that in C, and so forth, iteration 2, iteration 3. And if you tile all these together, you get a very similar, with G4, you can start to tile all of these together, and what it actually ends up doing is collating all the data into a larger data structure that then can be processed simultaneously and all at once. So you can really think of this as syntactic sugar for writing vectorized code in an iterative style. Here's another example where we're going to do summation over a vector. In this example, again, all the columns of B can be summed all at once simultaneously with using G4, whereas the regular for loop would have to do that in separate kernel launches one at a time. The next advanced concept to talk about is multi-GPU scaling, and this is something that you can really get a lot of benefit from in optics applications. Workstations today can, standard motherboards often come with 2 or 4 PCI Express slots. There are even more powerful ones that have 8 PCI Express slots. So you can get 2, 4, or 8 GPUs in one single machine. And when you do that, you can often get very close to linear speedups almost with using all of those GPUs for your problem, depending, of course, upon the data size and the how much work you need to accomplish in your simulations. But here's how Jacket makes it so easy to just scale with new GPU resources. In this case, we're just going to create, we have a loop. We're going to create a random matrix X that's a 5 by 5 matrix. Then we're going to run an FFT on X and store that in Y. Well, the way you can use multiple GPUs is through the gselect function. Gselect, if you pass it an integer, will select the GPU that's assigned to that integer. So in CUDA code, you have a GPU 0, GPU 1, GPU 2, and so forth. So gselect, you pass it an integer, it automatically will mod by the total number of GPUs. So if you pass it an integer that's higher than the total number of GPUs, it'll mod that back down and do a round robin situation. But with this for loop, essentially that gselect function is going to, for every iteration, assign the computation for that iteration to a new GPU. And it's going to then quickly assign, this for loop will just run really fast, assign out all the work to however many GPUs you have in your loop, and then all the GPUs will compute simultaneously until done. And again, the only difference between this code and single GPU code is the addition of that one-line gselect that enables that multi-GPU computation. Okay, so now I want to step back. Well, actually, let me address some of the comments that have come in. Let's see here. Okay, so there was a question about, this is a question that relates to licensing. So with Jacket, there is a free 15-day trial that is available. And that free 15-day trial includes a license for all of the features of Jacket, so which includes the multi-GPU ability to scale up to multiple GPUs simultaneously. Now, when you purchase a license, this multi-GPU scaling is a separate addition to the standard Jacket base license. So the feature is called Jacket MGL for multiple GPU license. And if you only have that for one GPU, then if you have 3 GPUs in your system, you're only going to be able to use that first GPU. But if you're licensed to use multiple GPUs, then it will work and run on all GPUs simultaneously. There's also a question here about the relationship between this kind of loop where you're doing a for loop with gselect as opposed to using the parallel computing toolbox's par for loop, which you can also use. You can use par for, and then inside of par for, do a gselect or do a just regular Jacket code inside of that loop, and it will assign, it can likewise assign the computation out to the GPUs. The difference is the following. With a par for loop, you can do, par for creates heavy CPU threads, so it creates the ability to, or it'll create many CPU threads for however many you allocate in your MATLAB pool. Now, these CPU threads are heavier, and that means they're slower. They're not able to toggle between multiple GPUs as fast as the code on the screen is able to with the gselect function. But they're able to do more. They're more versatile in that they're able to mix CPU computation with GPU computation through Jacket. You can do both. You can have par for, and then inside of par for use G doubles, and you can mix those G doubles in the body of a loop with other CPU computation in that same body of the loop. Whereas in this code that I have on the screen, you're only creating essentially different threads for GPU computation, but the CPU computation does not, it all remains on the single CPU thread. It doesn't get split up into multiple threads. So that's the way to think about this, is there are different kinds of approaches. You can mix and match CPU parallelism with GPU parallelism. It's all compatible, but depending upon your application, you may want to not use par for, and you may want to just use the gselect, as we show here, or you may want to use PAR4 in addition to G doubles and G select to be able to really, get sort of many layers of parallelism into your problem. And so that's the way to sort of think about it. You really have a lot of options here. Let's see. Some of you have asked questions about your specific code, and we'll follow up with you in a personal conversation after this to make sure. Some of you, it looks like, have even tried some of this and have questions about it. We'll follow up with you personally about this following this phone call. Okay, moving to the next. The next topic really is we want to explain. It's important, a big question we get is, why would I go purchase Jacket when, from a third party, from accelereyes, when the MathWorks themselves offers GPU computations inside of the parallel computing toolbox and distributed computing server. And so, it's important that you understand the technology stack so that you really understand how big of a difference it is between the two offerings. And so the technology stack of Jacket is really involved. And what it is 3 layers. It has a core runtime that does memory management, binary handling, GPU multiplexing, thread management, a lot of stuff that makes for the brains of the system. The next layer is the just-in-time engine that enables really lightweight but important and critical functions such as plus, minus, times, BSX fun. It enables those operations to be fused together into large, healthy GPU kernels, as opposed to launching one at a time and incurring all of the overheads that are involved with launching one at a time. And finally, there's the heavy lifting functions. These are functions written by our GPU experts that really take a lot of thought, and you write those directly in CUDA with a lot of optimizations for each one of those, and those are more heavy lifting functions. In order to get really good GPU performance, you need to create and launch healthy GPU kernels or beefy GPU kernels as much as you can, and avoid the overheads that are associated with memory management, memory movement, and kernel launches. All of these things, if you just had a collection of GPU functions, you will often end up with maybe every individual function is fast when it stands alone, but when you actually go to run a real application, the overheads in gluing the functions together to make things run are just tremendous. And so that's where this core JIT engine and calls, the combination of this technology stack, is what makes Jacket so valuable, and it's not available in any other application, including the parallel computing toolbox GPU features. So it's because of this technology stack that customers have, across many different industries, have experienced such large performance benefits. And here's a selection of those. Again, these are all GPU speedups that have been made possible through Jacket from anything from neuroimaging to medical devices to radar imaging. Even Google, in some Street View applications, was able to get accelerated video processing. They're trying to blur faces and do things that are important for privacy reasons. And so it's just really cool, all the applications that are occurring. So here's now a comparison with the parallel computing toolbox. The latest comparison is against the R2012A parallel computing toolbox. There are 4 things to say about that. One is Jacket is a lot faster. The second is Jacket does not use Java. The Java runtime introduces a whole extra layer of overheads, and the parallel computing toolbox is built directly into those overheads, and so that causes a lot of slowdown. Jacket is much more mature than the parallel computing toolbox. It's we've been around more than 5 years now doing GPU computing. The Parallel Computing Toolbox didn't start GPU until 2010, and Jacket includes much more functionality, so you can actually do many, many more functions with Jacket than you can do with the Parallel Computing Toolbox. So to quantify some of this, some of our partners have run some benchmarks. These are all actually individual function benchmarks. They're not actually what I was talking about previously, where you have an application that glues everything together. This is just looking directly at the overheads involved with real simple functions like cosine. Cosine in Jacket is 76 times faster than the Parallel Computing Toolbox. And sorting and convolutions and the simple times element-wise multiplication. I mean, these are just tremendous differences between the two. And in fact, there's such outrageous differences if you benchmark the Parallel Computing Toolbox against the CPU, you'll find that it's actually slower, that the GPU functions that they deliver today are actually slower than just using the CPU. So it's really just a waste of time to try to use the GPU computing features of the Parallel Computing Toolbox. Jacket is more capable. It's got linear algebra image processing, signal processing, and statistics, just much, much more than is available with the Parallel Computing Toolbox. It's got a graphics library that Parallel Computing Toolbox doesn't have. Supports all NVIDIA CUDA devices. It supports OpenCL now, though in beta form. We will have some exciting announcements on that coming up later this year, but it's really pretty cool. Supports all versions of MATLAB, including older versions. Again, you don't have to purchase the Parallel Computing Toolbox to use Jacket. And again, the G4 loop is something unique to Jacket that's not available in the Parallel Computing Toolbox. Jacket has 10 times more functions than the Parallel Computing Toolbox. Here's a list of the functionality that's available. You can just look at the function list, though, and see for yourself. We're talking about thousands of functions and function syntaxes that are supported in Jacket, relative to a little over, around 100 or so of the Parallel Computing Toolbox. Another benefit of using Jacket is that it's really easy to maintain. So GPU technology is expanding at a very rapid pace. This year we will see the release of, and we've already started to see the release of a new NVIDIA GPU architecture called Kepler. Kepler has many, many different features than the previous Fermi architecture, and Fermi had many features different than the Tesla architecture that came before it. So within just 5 years, these are 3 different architectures that are wildly different from each other. And the nice thing about developing with Jacket is that once you develop your application in Jacket, you don't have to make any code modifications to leverage the evolving hardware. You simply upgrade the version of Jacket that you use, and those versions automatically support the new hardware features that come from these platforms. So we have customers that we started selling, we started a beta version of Jacket in 2008. We have customers with code from that 2008 version that haven't had to do anything to their code, and it still runs with great performance in the latest version of Jacket. Okay, now that we've talked about MATLAB code, I know that many of you that develop optics applications ultimately want to go to something besides MATLAB, such as C++, Fortran, or Python. For that and for a lot of reasons, we have started developing ArrayFire GPU library. ArrayFire is a different sort of model. These C++ and Fortran and Python, it's sort of a different world than the MATLAB world. And so it's got a different model. It's actually a free GPU library for single GPU purposes. free, and that actually means most users, as most GPU users are only using a single GPU today. And it's available as well for CUDA, and there's a beta version for the OpenCL devices. The same exact concepts exist in ArrayFire, where you have a new data type. In ArrayFire, we call that an array, as you see in green. This is the same exact example that we showed in MATLAB code previously, where functionally we are estimating pi. And so in this example, you create an array, and then you can use all the functions that exist in ArrayFire, which are expressed, again, as very simple mathematical commands, and don't get confused with all of the low-level details required for GPU computing, but you can get all that benefit with the ArrayFire GPU library. Okay, so with that, we will end the slide portion of this discussion. And again, we encourage you to go to the website and try a 15-day free trial of Jacket. Now we're going to go to more of a demo sort of portion of this webinar. So what we're going to show is some of the very common optics applications that we see coming in. The most common are boil down to FFT sorts of operations, as well as interpolation sorts of operations. So we're going to show how much benefit you can get both on single GPU applications as well as multi-GPU applications on this. First, we're going to start by just going to accelereyes.com. And I want to show you quickly how you can find some optics sorts of information. As far as Jacket goes, you can go to the Examples tab. And in the examples, there are some interesting ones that would be related to some optics applications. There is, for instance, some Laplace transform applications that were done by Acunum Algorithms and Solutions. Let's see. Some biomedical infrared spectroscopy applications. It reduced hours of runtime at the University of Manchester. So you can look at that application. There's a lot of sort of filtered back projection, and this is a really cool application for using microwave tomography to image vegetation. Sort of interesting application. Digital holography for imaging. Just a lot of different interesting applications coming out of the optics space. So we encourage you, and again, these are just enormous speed-ups that this domain is seeing, from 17x, 10x, hours of runtime reduction. This one's a little slower, but that's because they were working on much smaller data sizes, 3.8x. So we encourage you to sort of search through those. In some of these cases, if you go to blog.accelereyes.com and search for optics, let's see. This is one where it has a video that you can watch about some optics-related things, as well as a link to a press article where this is dsprelated.com, and here are some speed-ups that they achieved. It was an older version of Jacket. Things have improved since then, but still FFT2 you can see is giving, at the higher image sizes, over 8x speed-up. And then in TERP2, again, at higher image sizes, getting up to an 8x speed up on some of these, pretty standard MATLAB functions. So that's interesting information that you could look at. Again, there's a list of case studies there that you could look at on the blog. In terms of learning how to accomplish how to get started and accomplish the tasks, that would be wiki.accelereyes.com. And on this page, there's a lot of tutorials and examples of how to get stuff done, jacket overview, getting through the installation, and then some jacket by example, jacket basics, G4. There's another feature called Gcompile. And then each of the domain areas, signal processing and image processing, for instance, even some optimization would apply to optics, are available there, and you can look through those details. Okay. One of the things I wanted to point out on the blog, if you look up the word wave, you'll find a beam propagation methods. Here is some really nice source code that you can download directly from the blog post that you can run yourself. And this was a code that appeared on the file exchange on MATLAB Central about beam propagation methods, and they use the parallel computing toolbox. But if you run this with Jacket, you can do some comparison yourself of Jacket versus the parallel computing toolbox. And here's a zip file with the code that does that. So that's a really cool way to sort of run really quickly yourself an optics sort of application and see how it compares. We're going to post the code. We're going to do a blog post with a recording of this webinar, along with code that you can run yourself in order to be able to do some benchmarks on the FFT and interpolation. We have the machine all ready to run here. It's just not connecting to or it's disconnected mid-session here from the WebEx. I'm going to answer some of these questions just verbally here that have appeared in the chat screen. There's a question that says, for multiple GPUs, can GPU RAM be combined to make a contiguous RAM space? And the short answer is that no, you can't do that sort of, well, it just depends what you mean by that. Natively, no, they're all separate RAM spaces, but there is this concept of Jacket managing all of that memory for you. So again, with that gselect function, you don't have to do anything specific to manage the memory separately amongst the various GPUs. It's all handled automatically by Jacket for you. So in that sense, yes, Jacket manages all of the multiple GPU memories for you. But the big caveat there is that you can not, and yeah, that's right. The question was, so the largest data set is determined by RAM on a single card, and that's exactly what I was going to say. Yes, the biggest caveat is you cannot allocate one single GPU array that gets distributed across multiple GPUs. That's not supported today. That whole concept of doing distributed arrays across GPU processors is something that is in GPU computing software just beginning to appear in some academic projects. We look forward to supporting that commercially in all of our products, but it's just too new right now to support. It's just too cutting edge and not fully supported by any projects currently. But that is something that we believe will be coming as a feature in the near future. Okay, the next one is, what is the largest GPU RAM space supported? And that then depends upon the actual GPUs that you have in your system. The largest GPU memory available in a single card today is 6 gigabytes. Those are the Tesla C2075s, I believe, are the latest version of those. There's C2070s as well, and M2090s for the servers.
Those have the largest memories today at 6 gigabytes. We don't know yet what the max memory size will be of the Tesla Kepler products, at least the main Tesla Kepler products, which have yet to launch and are expected to launch toward the end of the year, perhaps around the supercomputing time frame of November. If you have any other questions, feel free to post them into the chat window. Otherwise, again, we'll make this presentation available through our blog. And so if you subscribe to the blog, you'll see that. And we will post the code that we were going to run on this machine that seemed to be stuck not on WebEx. We'll post that code there so you can run it with a trial version of Jacket on the screen. Here's a couple more questions. In G4, iterator works on independent blocks iteratively. Can I do if condition to some parameters inside the G4? And that's a good question. The G4, best place for learning about the things that you can do with G4 is to go again to wiki.accelereyes.com. You'll come to this page and then click on G4 usage, either here or it's also in the sidebar. And then there are all sorts of usage scenarios. These are things that you can do with G4. And then there are restrictions, things you cannot do with G4. One of those is about the if statements, which was asked. So no conditional statements. And so the problem is, no, you cannot do an if statement inside of a G4 loop like this. But what you can do is there are often solutions to work around this kind of problem, where you can do an implicit if statement through some just smart arithmetic. And so, so this is one example piece of code that you could just modify in this manner, and you would be able to get the same result. Same thing here, this sort of problem and this sort of solution. Again, the issue with the if statements is that it's going to launch all of these iterations simultaneously, and so each iterations, the work that is done in each iteration needs to be the same for each iteration. So if one tile is going to do something different than another tile, then you can't combine them into GPU kernels. It just doesn't. It wouldn't. The algorithm wouldn't work that way. So that's the fundamental restriction and the reason for that. But as long as the kernels that you're going to run across the data in each iteration are the same, then you can launch that sort of problem. Okay, next question. Are dual GPU cards treated as one or two GPUs? So to explain that, for those of you who may not know, sometimes NVIDIA offers a video card that you can purchase that actually contains two chips on one video card. Jacket relies upon CUDA to determine how many total GPUs are in the system. It does a sort of a device query to figure out how many total GPUs are in the system. And from a software perspective, you don't necessarily even know that there are multiple GPUs on a single card, or if there are all separate cards. It just sees all of the CUDA devices as unique entities. And so yes, if you have two GPUs on a single card, those are counted as two GPUs, not as a single GPU. From the software licensing perspective, the software just knows how many CUDA devices there are. It doesn't know how many physical video cards you have plugged in. Let's see. So back to the question about G4 and asking, so in block reconstruction algorithms, you may have some, you may be doing it iteratively, in which case for some blocks you may want to stop those iterations at one point, whereas for other blocks you want to continue those iterations until convergence or whatever. This is a very similar sort of algorithm to ordinary differential equations, such as like the ODE 4-5 problem, where you are taking time steps of a certain length, and those time steps you don't know beforehand how many you'll need to converge, and so you know, some Monte Carlo simulations similarly. There are ways to work around those problems. It's I don't have slides prepared to discuss that right now, but in those problems where you're running essentially many small problems, each of a variable time step, you can use G4 in smart ways to accomplish those. We would encourage you, for those of you that asked that question, to contact us at support@accelereyes.com, or contact us on our forums is an even better place, and we can help point you to the resources for how to accomplish that. Okay. With that, I believe we've come to the end of the hour block here. We certainly appreciate you joining this WebEx webinar, and we look forward to working with you and to making your code faster. Again, feel free to contact us if you need anything. We will be more than happy to speak with you about your optics applications. Thank you and have a good day.